All right, this video is going to be on total internal reflection. So we're at this point in the notes, but I'm going to show you a demonstration of it first. And this simulation shows it really, really well. In this simulation, I have a laser. In this case, it's starting out in water with an index refraction of 1.33 going into air with an index refraction of 1. And that's going from a slow material to a fast material because the bigger n is slower. And when that happens, we should kind of remember that the angle is larger where it's faster. So the angle over here in the air is bigger than the angle in the water when we measure from the normal line. So this is about 40, and down here this is maybe 57, 58. Now, there's something interesting that happens. If I start out with a really small angle, all right, very little of the light gets reflected off of the surface. Most of it gets refracted. But as I bring this down, you'll see the reflected ray kind of gets a little darker. That means more of it is being reflected than before. So as it gets lower and lower and lower, okay, I get more and more reflected. And we see that with sunlight. When the sun is going down over water, as the sun gets lower and lower and lower, you see more reflections off the water. Now, in this particular situation, when I'm going from slow to fast and theta 2 is bigger than theta 1, what's the biggest theta 2 can be? It's 90 degrees. And as I pull this down, I eventually get theta 2 to be 90 degrees, and now none of it gets refracted, it all gets reflected. And that phenomenon is called total internal reflection. So, total, meaning all of it, reflection, and then internal, meaning it stays in the water, it doesn't go into the air at all. Now, this turning point angle up here, the angle of incidence where that happens is called a critical angle. If I'm below the critical angle, I get some reflection and some refraction. Then I hit the critical angle, which is about 49 degrees, okay, or 50 degrees, right about here. Now, this has gotten to be 90 degrees, and it's all reflected. And then for any angle bigger than that, it's all reflected. Okay, so both reflection and refraction get past the critical angle, all reflected. So for total internal reflection, we are going to say that when light travels from a slow to a fast material, there exists an angle of incidence called the critical angle, where the angle of refraction reaches 90 degrees and all of the light is reflected. And this is called total internal reflection. All right, and so here's our example. We are going to say that this up here is water. N is 1.33. And this down here is air. N is 1. And we're going to ask the question, what is the critical angle? All right. And to do it, we're going to use Snell's law. So in here, we're going to say N1 sine theta equals n to sine theta 2. And then we're just going to plug in. All right, we have N1 is 1.33 because it's the water, times the sine of theta 1, because that's what we're looking for. Equals 1 for water times sine, and then we set theta 2 equal to 90, okay, because we're at our critical angle when theta 2 equals 90 degrees. And we get 48.75 degrees. Which is what we said when it was about 49 degrees. So going back over to here, right, if we're above that 48.75 degrees, I get both reflection and refraction. As soon as I hit that critical angle, it is all reflected. Now, what if I went the other way from air into water? So I'm going to change this first material to air, and then the second material to water, and see what happens. Does a critical angle exist? So as I'm going this way, all right, I have reflection and refraction, I have both, okay, until I get all the way over to here. So no, it doesn't ever happen, okay? The reason why is theta 2 is less than theta 1, so theta 2 is never going to be 90 degrees, so it's not going to happen. So we'll make a note of that too. All right. Will total internal reflection occur when traveling from a fast to a slow material? The answer is no, because the angle of reflection, refraction, is less than the angle of incidence. So it will never reach 90 degrees. So if I'm going from slow to fast, all right, then it does occur because theta 2 is going to be 90 degrees, and that's how I find a critical angle. I set theta 2 equal to 90 degrees. Oh, and I have this backward. This should say, oh, that's right. And then here, if I'm going from fast to slow, so instead of going from water into air, I went from air into water, okay, it's not going to happen because I can't get 90 degrees.